Hello everyone, I am Shresth, and today I'll present common pitfalls and optimizations for modern cryptographic protocol implementations. Just a disclaimer, I'm not a cryptographer. I am just a crypto enthusiast who has been working with a bunch of cryptographers and blockchain scientists to audit cryptographic protocol implementations. And this talk is sort of a rant on how our space is moving and exploding and building so much new cryptographic primitives with so much added complexity, but our engineers are still very slowly picking up, and maybe they don't even talk the same language, and things which are obvious to one side is not so obvious to other. So most of the things that I'm going to present is going to be much more intuitive and simple than what you guys have probably heard during the day. Let's go on. So first I'm going to present two sort of pitfalls. So first is, let's say, prime fields, right? These are very nice algebraic objects. We use it a lot in cryptography. And I mean, intuitively, these are very simple, like similar to just having an integer, but then it just wraps around once it reaches the order. So let's just build a simple implementation to just warm up, right? You have a FP, a prime field, with order P, which is, let's say it's a 128-bit order. And then for now we have addition and subtraction, and it's very simple. We just add and then do a modulo P, and similar for subtraction as well. The only thing is it might overflow, right? So you need to make sure that you typecast it to a bigger type so that it doesn't overflow, then do a modulo P, and then you can get it back to your original type. And for the subtraction, you can have negative values, but in a prime field, it wraps around, so you can just do a P plus so that you can get the negative values. You can use just the uint value to also represent the negative values. So this is quite simple, and if you would find some definition somewhere, this is probably how it's going to be written. But then let's put some more engineering functions to this implementation, right? Some things that probably a cryptographer would not mention it on his paper. Right? So we put, let's say, serialize and deserialize. So you have, we wanna use a byte 16 for serialization and deserialization. So serialization is simply, you take your FP, and as it is, you can give your byte 16. But then let's have a deserialize. And for deserialize, so for all the operations, we are just doing mod P. So we get the bytes, we check, we convert it into U128, and then we do a mod P, like everything else. Very intuitive. And now we've built a big protocol, and we've raised a lot of money. We want to do an airdrop. So we build a protocol where we have a claim function, and we will use our FP implementation. It's very simple. We have a nullifier. You can pass your field element, and this checks if this, the airdrop corresponding to this field element has been claimed or not. If it is not, it throws an error. Otherwise, it deserializes using a deserialize function, does some operations, and gives you the money. The developer was very happy. He thought that he built something cool. What's the catch here? Anybody? Do you? Exactly. So, as he said, if you look carefully, right, the wrapping around and this deserialization is a problem, because what's happening is essentially there are some numbers which are bigger than P, but once you do the mod operation, it wraps around. So there are some small numbers which have two different representations in uint 128, right? This is exactly I think there's multiple ways to fix it. One of the possible ways is to just fix deserialization. So only allow for canonical, canonical representation, which is you have one-to-one mapping. If you do it this way, then you can make sure that higher level protocols don't have to think about it, right? The fix is very easy. You check if the number that you got is actually lower than the order. Otherwise, you throw an error. Okay. Now, this is another similar problem, but it's a little bit more tricky. So you want to do, uniform randomness, and you again do the same thing, right? You just sample 128 bits, and then you just do a mod p. Now this is biased, right? Because again, you have the wraparound problem. And this is the fix for it. So you can just sample unless you get a number which is lower than your order, and then you can use that. So generally, the first sort of pitfall that I would like to conclude on is for serialization and deserialization, we need unique representation. And this is kind of operation that sort of a cryptographer would not mention clearly on his paper. He would just say, okay, this is sent over the network, but then an engineer has to implement it out, where you can have these kind of mistakes. This leads to the second pitfall that I want to discuss. Frozen heart, the death of Fiat-Shamir heuristics. By the way, the death of Fiat-Shamir heuristic was not said by Jim Miller. I just added it to make it sound a little bit dramatic, as if it's a movie, whatever. There was a talk by Open Zeppelin this morning on a similar issue. Fiat-Shamir, the problem with Fiat-Shamir has been known since 2012, when there was clear discussions on weak and strong Fiat-Shamir. But we are still in 2024, 10 years after that fact, and we still see implementations doing it wrong. So I think people are still missing the intuitive understanding of where this protocol lacks. Okay, so I'm going to try to build a little bit of an intuitive understanding here, and I'm going to use some nice graphics by the Trail of Bits team. So you have, let's say, a prover and a verifier, right? And the prover wants the verifier wants to know if the prover is a good tennis player, right? And the prover wants to convince the verifier if it's a good tennis player. So what they do a game, right? So they play a game where the prover plays against the verifier, and every round the verifier tries to give the most difficult shot it can, right? And after a few rounds, if the prover can actually play against the verifier, he can be convinced that he's doing a good job. And the verifier is convinced that the prover is a good player. Okay. But then, prover doesn't want to sweat, right? So he doesn't want to get out of his house. He just want to, let's say, know if the prover is a good player or not. So he's fine watching a stream of the prover playing. So he can tell the prover to play against the wall, right? And he keeps playing against the wall. And as long as, wall somehow magically, is returning right or is returning random moves to the prover, after some rounds, even if the verifier just saw like a video of the prover playing, he can be convinced that he's playing a reasonable game. Let's come back to the cryptography world. For us, we have prover, which is, so exactly this is what Fiat-Shamir does. So you have most of the, Yeah, so most of the cryptographic protocols, most of the zero knowledge protocols, or even SNARKs, they are originally interactive, and then you apply this Fiat-Shamir heuristics to transform them from interactive to non-interactive. And the way you do it, and the wall here is our hash function, aka random oracle. There's question of if it's actually random or not, but even if it is, the issue comes, so again, coming back to the tennis analogy, if for some way the prover knew a particular angle where he could throw the ball and get the ball back in the same angle or in the same velocity, he could just game the system by like doing the same move again and again. And similarly, in case of Fiat-Shamir, if you can somehow figure out, you can bias what the output is, you could break the system. So I'm going to give a concrete example here. So the easiest protocol to explain this is the SNARKs protocol, which is, let's say you just want to prove the knowledge of x for, so y equals to g to the power x. So you just want to prove the knowledge of an exponent, and here you can just say y is your public key and x is your private key. The SNARKs protocol is quite simple. You can, basically in the interactive version is you ask the verifier to give you a random value, and then the prover itself generates a random value a, and sends b equals to g to the power a. And after that, the verifier replies with a random value c. The prover then sends z equals to a plus cx, and then the verifier can check on its local. Most of you guys are probably familiar with this. Now we can convert this into non-interactive version, and we can do this by, let's say, an incorrect transformation first, which is, just the step where the prover waits for the verifier for the random value. He can just generate it locally by using this random oracle. So it just asks the random oracle, here is my B. So with the B, and it's for now it's just a hash function, you get the random value C. Okay. But then, because somehow your public key is not really linked to the random oracle output, you can compute a public key after the fact that you have this random oracle output, even though you don't know the exponent or the private key to that public key. And you can do that as follows. Just pick a random B, generate a C for that using hashing, and then you can compute y equals to g to the power z divided by b to the power 1 over c. You can do the math, it works out, and then in the end, if you send that to the verifier can check and be convinced of this. This is similar to how, when you write the zero knowledge property of the Schnorr's protocol, when you generate a transcript, this is exactly what you use to prove it. Just to fix that, the correct transformation here would be that the hash should include both y, g, and b, so the public key, the generator, and the b. So this will make it a strong Fiat-Shamir instead of weak. So this brings us to the rule of thumb. This is the most important part here. So essentially, the Fiat-Shamir heuristic, the oracle, should include all the public values. And not only that, it should also include all the intermediate values generated. So all the commitments that are generated during the interactive process should also be included in the Fiat-Shamir for every nth round. Okay, so now we've done some pitfalls, and now we'll go towards from ranting to actually optimizing things, and seeing how we can use engineering to optimize the cryptography. So we have this threshold trick that comes again and again in several protocols, including Shamir secret sharing, DKG, Reed-Solomon coding, where you have m parties and any n of them can come together and then recover some information or some secret. And just to give a primer how this works, it's quite intuitive and very nice. You essentially want to encode your information in a n-degree polynomial. So your coefficients is your secret, or just information. And then you sample m points from this polynomial, and as long as any n parties come together, they can interpolate the polynomial and recover the secret. And this is a very elegant trick that is used in several places. So the steps are, first you have to generate this polynomial, which has the coefficients as your information that you want to encode. Then you want to sample, let's say, consecutive points that you want to distribute to the people. And then these people can come together and do some interpolation. Okay, so the usual implementation of, let's say, evaluating these polynomial to generate these shares use Horn's method. And this we have probably learned in our algorithms class. If you want to do a polynomial evaluation using Horn's method, you can get from n square multiplication to just n multiplication and n addition, which is quite easy. But to generate m shares, right, you need n times m's multiplication and n times m additions. So if you think about a blockchain system, this m can scale, right? As the number of nodes are growing, the number of shares you want to sample will also grow. So can we make this better? Can we somehow remove this quadratic factor from n times m, essentially? So I'm going to explain an approach which I've not really seen before in cryptography, the finite difference method. And the idea is we will use the finite differences to calculate the next consecutive evaluations without paying for multiplications. So it works as follows. Let's say we create a simple table. And for the first n evaluation, we just use our Horn's method. So we use our Horn's method to evaluate the first 5 indexes. And now we want to figure out what's the 6th index without paying for multiplication. So first we calculate the finite differences. And the finite difference is essentially let's say if you take D1, so D1, the D11 is essentially D11 is essentially the F2 minus F1, which is 1. So essentially it's the difference between the two entries of the column in the left. And you can keep doing that until you get this. It's just subtractions, which is equivalent to doing additions. And then once you build this table, what you can do is, you know that we can observe that the finite difference of the nth will be a constant and the n plus 1th will be just 0. This is similar to derivative, right? So if you take the nth derivative, it's a constant, and the n plus 1th derivative is just 0. And once you have built this table, what you can do is you can use this to calculate the next entry by just adding the consecutive values. So now we start doing it from right to left. So for D4, 2, it's essentially summing up 0 and minus 19, getting minus 19. And then for D3, 3, it's essentially minus 19, minus 3, giving us minus 22, and so on. And now if you keep doing that, you get the 6th value. And this is just doing additions, right? So now we're no more paying for multiplications, and you can keep evaluating this for m entries. So now somehow you have moved away, now the complexity is moved away from n times m multiplication to just n square multiplication and n times m addition. This was a trick I saw in a compiler's class for removing invariance, and somehow it applies here as well. Okay, so this brings to the last optimization that I want to talk about. We all know that the native operations are very fast in computers. So like if you want to do a native multiplication or an addition, it's very fast. But then whenever you want to do a virtual operation, like a group operation or some other cryptographic object operation, it's slow. Or in terms of circuits, you can think that when you perform an operation in the native field, it's very fast. But then if you perform an operation in a bigger subfield, it can be much slower. So how can we optimize that? And to do that, a very sort of intuitive trick is to just use the native operations whenever you can and only fall back to non-native operations when really it's needed. And for that, I'll just show an example of how you could do it for Lagrange interpolation. So in Lagrange interpolation, again, you need n consecutive multiplication, and the native multiplication is 20x faster than a BLST scalar multiplication. So here is an implementation, and essentially the idea is you have the values as u in 128, and you can multiply them. If you check if you can multiply them in the u in 128 if it doesn't overflow, and if you can, then you simply multiply it. But if it overflows, then you convert it into scalar and then multiply it in the scalar field. So instead of doing a normal multiplication here in the reduce, you have two different accumulators. One is the scalar part of it, which is actual value, and then there's the remaining one, which is still in u in 128. So every time you have a value, you check if it overflows, and if it doesn't, you multiply it. And in the end, what you get is the remaining in the scalar, and then you can multiply the scalar, you can multiply the remaining, convert it into scalar, and multiply it with the accumulator. So this essentially, speeds up the concrete implementation. I would like to credit Miston Labs, because a lot of work I presented here was inspired from audits that we did from Miston Labs, and also the Frozen Heart pictures, and also the discovery was done by Trail of Bits. So I would like to credit them. And in the end, I would like to leave you guys with this note on translational cryptography, that the space is growing quite a lot, and we need more people that can understand, more engineers that can understand cryptography, and more cryptographers which can understand engineers. And we need to build more documentations, not just white papers where we explain in details what checks and what constraints have to be built to build these systems in production. I I'm happy to talk more about this and discuss if you guys have interesting findings and optimizations. Yeah, thank you.
Any questions from anyone? Yeah, up there. Okay.
The one that you said the randomness is biased. I saw in the ED 25519 paper that say if you have 61 bit extra, then it's okay.
Yes, there's another fix you could do. That you could take enough bits and then it's not a problem. So this one, it's a problem because we're just sampling 128 bits, but if you take sufficiently more bits, that's again, is not a problem. It's another way of fixing it, yes.
Can you give a Fiat-Shamir failure example that you omit public values and it fails? Like, if like the point and the curve, both the verifier and prover knows which point is it?
I didn't understand your question. Can you repeat?
You said the Fiat-Shamir needs all the intermediate steps plus the public values, right?
Right, yes.
But if the verifier and the prover, they agree, like, if the public value doesn't change and everybody knows them.
I see. I'm not sure. Maybe it works out.
Okay.
Yeah.